Okay, I'm going to go through the 9.1 quick check. Now, first thing to start off here with about light and waves, notice that we have all of these equations, and those are things we're supposed to understand. So the idea is that if we talk about the wavelength of a line, if we talk about the frequency, if we talk about the energy, given any one of those, you should be able to go back and figure out the other two. And for those, we're going to need speed of light, okay, and we're also going to need Planck's constant. So those are there for us, and then we use these equations. So first question here, consider this graphic of a traveling wave of light, scales nanometers. Okay, what is the wavelength? Well, we know wavelength goes from crest to crest or trough to trough. So we can kind of figure here we're going from 300 to 800, so this is going to be a 500 nanometer wave. Now what's the frequency? So the idea is if we know that the wavelength is 500 nanometers, we want the frequency. So we're going to use this equation here that says lambda times nu is equal to c. So therefore, if I want my frequency, that's going to be c over lambda. So like here, if I want this number, then I'm going to take my c divided by lambda, and now I just substitute in, and I'm going to say 3 times 10 to the 8th meters per second divided by 500 times 10 to the minus 9th meters, because that's what a nanometer is, and then I just have to solve. This comes out to be 6.0 times 10 to the 14th, and this is what we have meters on the bottom, so it's the seconds to the minus 1, which is what we call for frequency. So 6.0 times 10 to the 14th, seconds to the minus 1. You might also see this once in a while written as hertz, Hz. Okay. Next here, what is the energy of the wave? Well, we know the energy is equal to h times nu. Okay, Planck's constant is 6.6, let's go back and look, 6.626 times 10 to the minus 34. And this is joules times seconds, so that's h. And we just figured out that this is 6.0 times 10 to the 14th seconds to the minus 1. For this, I get 3.9756 times 10 to the minus 19th. And we can see that the seconds are going to cancel, so this is joules. And I would report that maybe as 3.97. Actually, you probably would say 4.0 times 10 to the negative 19th joules. Okay, so we can see electromagnetic radiation with wavelengths before 400 nanometers and 700 nanometers. So could we see this light? Yes, we could. Okay, because this is 500 nanometers, and that's between those things. So yes, we could see this. In fact, I just looked this up on the internet. It looks like this would be kind of a green, nice green color. Okay, we go to our next question. Is consider the n equals 4 shell of an atom. How many subshells are in the shell? How many orbitals are in the shell? And how many electrons could occupy the shell? So we're talking about the nucleus, and we'd have the n equals 1 shell, 2, 3, and 4. So how many subshells? Subshells are the types of shells, and it turns out if n is 4, then there are 4 subshells. So what is it? We're going to have in the fourth, we're going to have the 4s, we're going to have the 4p, we're going to have the 4d, and we're going to have the 4f. So when n equals 4, there are n subshells. So the answer is 4. How many orbitals are in this shell? Well, we know for the s's there's 1, and for the p's there's 3, and d's always come in 5s, and f's always come in 7. And if we add that up, we're going to find out that is 16. And 16, you might notice, is n squared. So that's a shortcut, is always, how many orbitals there are. N squared orbitals, 16. Well, each of these orbitals can hold 2 electrons, so it's just going to be 2 times 16. So we're going to have 32 electrons that can occupy the n equals 4 shell. The last little piece, let's talk about the 4s and 3d orbitals. Okay, which orbital has higher energy Now this gets a little bit tricky. We have to go back to one of our diagrams, and I really like this diagram. And we can see here's our 4s, and here's our 3d orbitals. And the 3d is a little bit higher energy than the 4s. 3d is a little bit higher energy. So which orbital has higher energy? The 3d. Even though it's on the third floor, even though it's the third shell, it actually has a little bit higher energy because of the D shape. Now, which orbitals farther from the nucleus? Okay, that's easy because 4 orbitals are farther away than 3 orbitals. In our analogy, we're saying that's on the 4th floor versus the 3rd floor, and that's on the average, 4s orbitals farther away from the nucleus. Electrons are farther from the nucleus than if they were in a 3d orbital. Okay, write the orbitals in order of lowest energy to highest energy. And we have to have some technique to do this. And again, I like this chart. And so I remember that, I have 1s orbitals, I got 2s orbitals, 3, 4, 5. That the p's are a little bit higher energy than the s's orbitals. But then when you get to the d's are one orbital, up shell higher than the other. So a 3s and 3p, but the 3d's are up there with the 4s and 4p's. The 4Ds are higher up there with the 5S and 5Ps. So just keep that in mind. So if I'm going to do this in order, then the lowest energy orbitals, we're going to go 1S, 2S, 2P, 3S, 3P. So that part makes perfect sense. And then we actually go to 4S before we go to the 3D. 4S before we go to the 3D. There's 4S, there's 3D, next higher up. The next ones we have are 4P. Then we go up to the 5s, so we have 5s, 4d, 5p, and the next one we don't see there is the 6s. Now this chart then is one way to get the energies of the orbitals, and we can also go back to this, and we say, if we go by the diagonals, we have 1s, then we're going to go to 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and 6s, and that gets our answer that we have, and that is the quick check.